Thanks everyone for joining. My name's Andy Cirillo. I come to you from Conversant Media. We're a ad tech, martech data company. And today I wanted to talk about a subject that, at least before today, I felt was not getting talked about enough, but was becoming more and more important. Turns out when I showed up today that there's at least 2, maybe 3 other talks on a similar subject. So I think that's very encouraging. In fact, there's even a company has been built around some of the things I'm going to talk about, or helping companies do some of the things that I talk about. So it's very exciting, and I'm very excited to see that I think some of this is really taking hold. So data-driven engineering, or how I learned to stop worrying and love testing in production. So what am I talking about? And why is my thing not working? All right, just do it like that. All right, what is data-driven engineering? So it is the engineers using data produced by production systems in a disciplined and methodical manner to guide the development of new software. That means using things like scientific method, formal experimentation, and statistical analysis. To clarify some things that I'm not quite talking about, so I'm not talking about data science, although that's a very important and related field. I'm not talking about data engineering. I am not a data engineer myself, but I consume the output of data engineers, and I'm very heavily reliant on it. And when I was putting this talk together, actually, I debated with myself for quite some time about whether this thing called data-driven product management that is a thing. I was debating whether what I was about to talk about was an extension and enhancement of data-driven product management, or a different thing. I ultimately decided to call it a separate thing. But this is also a very closely related and interesting field. If you find today's talk interesting, you might want to look into that as well. Data-driven product management is kind of the, I'm going to grossly oversimplify it here, but kind of the idea of rolling out 2 different versions of your website and A/B testing or testing control testing them to get a more formal way of getting user feedback. So what I am here to talk about is software engineers using data to do their own jobs better. And I'll get into what that means a bit in a minute, and for some reason this is rendering all wrong. What happened there? There we go. All right, so why now? The main reason is that we're starting to see a lot more systems that look like this, or systems and scenarios. So I'm willing to bet that at least some of you are working on systems that have hundreds of thousands of users. Can I see a show of hands? How many people have hundreds of thousands of users? How many people have millions of users? Okay, so a decade ago, 2 decades ago, I mean that was extremely rare. Now it's becoming very common that developers are working on these systems that are have millions of people using them. What goes along with that is that these are built on very large scale server farms, distributed systems, and you get complexities associated with that and benefits. Thing I'm calling out that will become important later on is that you're running your code on lots and lots of identical systems. So you have lots and lots of servers that are running more or less the same code. The other thing is we have the tools, the infrastructure, and the motivation to collect, to store, to query, to analyze massive amounts of log data, event-oriented log data that's coming out of these systems. And everyone is interested in this data. So in other words, we are building these systems around data. We are providing data to our stakeholders as part of the product that we're building. And it is things that used to be fairly specialized. When I started out, a data warehouse was something that insurance companies had, for example, or maybe a credit card company. But now, pretty much everyone has a data warehouse, or either they have one or they're in the process of building one. So it's become very common. If you're running in a cloud provider, for example, you practically get this stuff for free. So to get a little more into specifics of the kinds of systems that I'm talking about, we're building systems that have structured log formats. So data warehouses need structured logs. Using formats, it could be comma-separated values. We use, for Conversant, we use Apache Avro, which is just a nice convenience. It's a schema-oriented log format. I do want to clarify, I'm not talking about debug logs. So we're not talking about log4j, we're not talking about SLF4j, that sort of thing. We're talking about, typically, you are logging the requests that come in and some information about the response that you send. Another way of putting that is it's event-oriented. Some details about the infrastructure that I'm talking about. You might be using Kafka, you might be using Flume. On the data warehouse side, you might be using a relational database, you might be using a Hadoop, you might be using a formal data warehouse. Now the last ingredient that will become important later on is this notion of a partial production deployment. So when I said that it's interesting that we're running our code on lots and lots of identical servers, one of the things that this opens us up to is that a production deployment is not an atomic thing. It's something that is done, if you do it one server at a time, could take several minutes up to several hours to complete. So, the systems that we work on take 3 hours, if you're lucky, to get through the entire server farm to deploy. So, obviously, in order to do that, we need quite a lot of infrastructure. We need continuous integration, we need continuous deployment, we need deployment code, we need systems to manage and monitor the deployments, and we also have a notion of a partial deployment. So, I'm going to structure this talk into two main parts. And the first one is going to be some pragmatic things that I think everyone should think about doing right now if you're not doing it. Fairly low-hanging fruit, to put it that way. And then the second part, I'm going to get into more advanced and kind of maybe sci-fi-ish scenarios, but some things that we do actually practice in Conversant that I think get very exciting. So, part one, testing in production, from the title of the talk. Who here thinks that this is a scary thing? All right, good. And we have some brave volunteers. Some of you might think I'm completely nuts to even be suggesting this. But to explain why I think this is an important concept, I'm going to walk you through a scenario. This is a test scenario that I grabbed off of Wikipedia. It was literally the very first thing that I found because I'm terrible at coming up with fake scenarios, but I'm good at stealing them. So Wikipedia on one of their pages had this as an example of a test scenario. Nothing here is really specific to Gherkin, but I'm using the Gherkin syntax because I think it makes some of what I'm going to talk about very obvious. So scenario is refunded items should be returned to stock. Given that a customer previously bought a black sweater from me and I have 3 black sweaters in stock, when they return the black sweater for a refund, then I should have 4 black sweaters in stock. It's a pretty typical unit test. It's very respectable. I write lots of unit tests like this. Works perfectly well. It is, however, limited, as are pretty much all tests, because it doesn't really describe what the business owner meant. So it's describing a test that you can run, but the requirement is really not that only black sweaters have this behavior, right? And they certainly didn't mean that this rule only applies between 3 items and 4 items. So in the second half, I've written something a little closer to what I think the users or stakeholders meant if we're going to talk about requirements instead of tests. Something a little closer to for all customers, for items and times, given that the customer bought the item at time Tn and I have X of those items in stock at Tm, when they return for a refund at time Tm, then I should have X plus 1 of those items in stock. That's what they meant. If anyone is familiar with first order logic, you might recognize that there's a distinction here between existentially quantifying and universally quantifying. So the first one would most likely be interpreted as existentially quantified, but what was really of interest was the universal quantification, right? So there's really no reason to get depressed by this. As I said, this is a great unit test. Nothing wrong with it. Perfectly good, because the second one is not something that you can typically execute, right? It's impossible because it doesn't specify enough. It's descriptive, but it's not executable. So, one way that I like to look at this is I like to think of tests in terms of doing 2 functions. One part of the test is I'm going to call the driver code. And the other part of the test or the other function of the test is the assertion code. So the driver code is what creates the scenario and sort of exercises the system, runs the code that needs to be run. And then the assertion code just tests to see whether the appropriate rules apply. And the reason why I think that's an important distinction to make is because in practice, the assertions or a notion of complete assertions, like if you can imagine writing assertions that cover all the rules and expectations of the system perfectly, that's actually relatively achievable. It's not impossible to imagine accurately capturing all the requirements if you allow yourself to use universal quantification. The driver part of it, however, is not so easy, and in fact is in most interesting cases going to be mathematically impossible because there are, for all practical purposes, an infinite number of possible inputs, and writing a test that covers every single one of them is not something you can actually do. You can think of this as somewhat analogous to the famous halting problem, right? So the halting problem is, if you think about it, it's extremely easy to define, right? It's, does this program terminate? Or if I was going to write this as an assertion, this program must terminate. But as we all know, that's impossible, in general, to prove. It's a very similar case here. So you can write your assertions pretty tersely and get pretty accurate results with that. Where testing is difficult is in coming up with the scenarios to sort of exercise that, the existential parts of it. So what we're going to do in testing and production is we're going to take advantage of that. We're going to take advantage of that notion that the assertions are relatively easy, driving is relatively hard, and we're going to split the test into the driver code and the assertion code. And since this is a system that is generating event logs, or event logging is a very fundamental part of this, we're going to try to write those assertions against the log output instead of writing them in ways that use the internal state of the system or use other factors. We're going to discipline ourselves, and we're going to try to write as many assertions as we can that can be written this way against the log output. And then once you've done that, you find that you can keep the same driver code that you've got in writing your unit tests and run that in QA, but then run the assertions now as a query against the QA system's log output. And if you do it this way, you find that you can actually run the same tests in production that you do in your QA system, because it's doing the same thing. It's just reading a log output. These tests don't necessarily need to know anything about what scenario was used to set it up. All that they need to know is that, for every returned purchase, the store count needs to be decremented. There's an analog to this requirement, which is that after every purchase, the store count should increment. I think it's kind of hard to think about those separately. But let's apply that to this example and see how we would do that. So we're going to need to add a couple things to the log. We're going to add SKU. So if SKU wasn't in there already, we're going to need to add it. Most likely it was there already. And we're going to need to add the store count. So store count is the current value of that particular item's count in the internal system. But if you're, if you're used to this kind of system, it's highly likely that your building department isn't running off of your internal representation of store. They're probably aggregating the logs and maintaining their records that way. So it's a good chance that this information is already in your logs. All right, so then with every purchase and with every return, we are going to log the current value of the store. We're going to do as I said, and we're going to split the tests into drivers and assertions. Queries take the place of the assertions that would otherwise be in otherwise automated tests. And you run this against your QA database, your production database, or production logs, or data warehouse, and you get a pretty good answer. In fact, you get a much better answer than you did with that, more procedural unit test that you would have written otherwise. And you get coverage for all different combinations of events. It doesn't matter whether it's not only looking at 3 to 4, it's not only looking at particular timestamps or whatever. And you'll get output like this. So I'll just run through a little bit of the code that I've written here. I'm running this against the log output. I'm doing a case. If it's a purchase, I do -1, meaning that it should decrement the count. If it's a return, I do 1. That should increment the count. All other things should have no effect on the count. I'm going to take a look at logs from the start of the day. I'm still going to filter it against only black sweaters for now. We'll get to that in a little bit. And order it by timestamp. And it doesn't really matter whether you're going to do this entirely in SQL or you're going to do this in separate code, Java code or whatever, or Python or whatever. But you can see it's pretty easy now. All I need to do is look at all of this and compare the expected effect to the next value. So if I have 100 and I'm decrementing, the next value should be 99. Easy peasy. When you run this in production, it works exactly the same as when you're in QA. All right, so at this point I want to address this statement because I'm sure somebody's thinking it. Call it the elephant in the room or whatever. And I've heard versions of this. So I don't test my code in production because I have unit tests. My unit tests tell me whether it works or not. There's no need to run the test in production, and if you're testing in production, that's a bad thing. That's a naughty thing anyway, right? I want to address that. Why should you test in production? Top 6 reasons. I started with 5, but then I thought of one more. That's why it's 6. You don't know all the scenarios. So we've already established you can't test all the scenarios. But I think the situation is actually a bit worse than that, and I'm going to suggest you don't even know all of the important scenarios. We're actually terrible at this. We're very good at thinking happy thoughts. We're way too optimistic. We like to daydream about how our company's IPO is going to make us instant millionaires. We're much worse about thinking about all the things that are going to go wrong. So it requires a certain kind of imagination, and it requires a lot of imagination to guess the things that are going to go wrong. We do put assertions in our code. We do put tests in our code, but we tend not to break those tests, because if we thought to write a test for it, we were also thinking about that when we wrote the code. What we really need to capture is the things that we didn't think of, right? So second reason, basically what I just said, your imagination sucks. You spend too much time thinking happy thoughts. Something I hear every once in a while is, well, product manager didn't tell me I needed to cover that case. Well, your product manager's imagination is not really going to be any better than yours. In fact, it's probably worse. So don't blame it on the product manager. Fourth reason, things can change. So scenarios that didn't come up before have a tendency to suddenly happen unannounced. And it's good to be able to run your tests against production data even days or weeks or months after you may have deployed the code, because things can go wrong even if you haven't changed the code. Number 5, you still don't know all the scenarios. I want to reiterate that. Number 6, production is just different. So production is always different from your QA environment. We try to make our QA environment as production-like as possible, but that's always an as possible qualifier, right? All right, getting back to where we were. So I wrote up this test, ran it in QA, now I'm going to run it in production. But the first thing I noticed is that this test actually fails when I run it in production. And why does it fail? Well, this is a distributed system, and because you've got hundreds, maybe thousands of servers, and good chance you've got servers running on 2 coasts, maybe multiple continents. This notion of a global store count is really not well defined. There really is no point-in-time global store count because your system is probably using some definition of eventual consistency. Because of that, you're going to get little weird anomalies like I've highlighted here, where the thing doesn't decrement or it increments twice. But later on, it catches up. That's what eventual consistency is. When we built the system, we already decided we were going to make that trade-off. So it's not a big deal. It just means that we need to relax the requirements, a little bit, because it turns out the requirement is not that every server in your system has the exact same value of store count at every single point in time. So we need to relax it a bit. But this is the first kind of call out here. We've actually discovered something by running this test in production that's important for us to test. So eventual consistency always has to have a bound, right? So the product manager says, they may say it's okay that things are out of sync for a few seconds or maybe even a minute, but they didn't mean that eventual consistency meant at the end of the month that would be reconciled, right? So we can take advantage of that knowledge and actually add some tests that will cover our consistency bounds. And the reason why this can only be done in production is I'm guessing that your QA system always has your little 5-node cluster is always going to have really great consistency. So you really don't find these kinds of problems until you scale up to enough nodes that consistency starts to become an issue. So what I'm going to do with that query to cover this is, instead of going every single line by line and saying every increment needs, the next event needs to be one higher, every decrement needs be one lower. I'm just going to say I'm going to sum all of them up, and they need to reconcile over some window of time. And you can pick whatever window is appropriate for your consistency expectations. And I've written some SQL that does essentially that. You can code review what I've written. I think it works. And then I said I was going to address the black sweater issue. So we can actually make this just slightly more complicated and just do a group by SKU here and do the exact same thing for all items. So we've now done something with just a few lines of SQL code that would be extremely difficult to reproduce in a standard structured kind of test format. So, to answer the question of why should we test in production, well, you can test a heck of a lot more in production than you can in a QA system with unit tests. So you should do it, right? All right, so some concluding thoughts in part one. Write your test assertions against log output. Log output is an important part of your system, and it's, you need to be testing it anyway. And since you're already testing your log output, take advantage of that and use it to write better tests for all of your functionality. Production covers many, many more test scenarios than you could possibly cover in QA. So, Conversant, I don't know if any of you have stopped by our booth downstairs. It says something about we're running like 3 to 4 million requests per second at peak. We're doing terabytes and terabytes of data per day. All of this is getting sucked into our Hadoop clusters and data warehouses. You cannot reproduce that level of test scenarios yourself. Production is a great place to mine obscure edge cases. Sometimes I tell people they may come to a bit of sloppy code, and we'll point it out, and they'll say, that's a one in a million chance that that's going to be a problem. Well, if you're doing 4 million per second, then 1 in a million is happening 4 times a second. You really want that happening 4 times a second, right? So it's a great place to get edge cases. Non-functional requirements. Open-ended requirements, non-functional requirements like performance, open-ended like this needs to work better than 10% or whatever. Return rates can't go above 10%. Or I'm sorry, that's a non-functional. Open-ended would be lower return rates or better. Better than higher return rates. Well, how do you write a test against that? In a QA environment, it's hard. In production, though, it's something that you can write tests that maybe starts to overlap a little bit with monitoring. And then the last part, important one, external behaviors and dependencies. External behaviors are not things that you can test in QA. So we integrate with a couple dozen different ad exchanges. And while there is a protocol, and a common agreed upon protocol between us, every once in a while someone strays a little bit from the protocol, and that can cause problems. You can't test that in QA. You've got to have tests for that look for it in your production systems. All right, part two. From continuous integration to continuous experimentation. So this is where it really starts to get interesting. I'm going to start this with another hypothetical scenario derived from our black sweater example. Let's say that you've been running your code for a while, and at some point around April 15th, there was a behavior change, right? And the account manager for black sweaters is completely freaking out because their return rates jumped, spiked, almost doubled on April 15th. So high return rates in retail, very bad thing. They're all narrow margin, and they're counting on things not being returned too often. If they get returned too often, it kills their margins. So that's why they watch it so closely. So you go back through your code release schedule, you see new software was released on April 15th, but nothing particularly interesting. All the tests passed, right? Also, curiously, no one has complained about return rates for any other products other than black sweaters. So what's going on? I mean, did you introduce a bug just for black sweaters? Well, one of the first things you're going to look at is you're going to look at overall return rates because, you know, as I said, this is important. You're probably monitoring it very closely. So you're always looking closely at the return rates. And you see no noticeable change whatsoever on April 15th. I left the dates off, but April 15th is right in the middle of the graph, right? Well, the next thing you're going to do is you're going to break this out by item. So we've already demonstrated, we've seen, you know, return rates jumped for black sweaters, but why is it just black sweaters? So I'm going to take a look at that, and I see a pattern that looks kind of like this. So if you look at that closely, you can see, you know, on average everything's about the same, but it looks like there's been some crisscrossing. You know, if I zoom in on some of that, you can see, you know, roughly about half of the return rates actually have jumped. Black sweaters just happens to have been the worst of them, but it did jump for several others, just not quite enough to, you know, alarm the account managers. But another interesting thing is that half of them have reduced return rates. What's going on there? And, you know, a few of them actually have no change whatsoever. All right? So now you're going to go back into the code, and you're going to dig a little deeper into what change happened on April 15th, and you're going to see something like this. All right, so someone was doing a refactoring, very light refactoring. They noticed that the product images that were used to build these product carousels, everyone know what a product carousel is. Just, you know, when you go to you know, product page on some retail site, and it shows you a picture of the product, and then there's like a next and back button, and you can see other pictures of the product. You know, it starts with the first one, and then you can go through the carousel and see, you know, other variants of it. So there's multiple product images for each product, and we can see that before the 15th, the code was not picking them up in any particular order. It's just picking them up, dumping them on the page. So which one was first was based on database order. We don't usually like to do that. We consider that, you know, usually bad practice. You know, I like systems to be a bit more predictable and deterministic. So, you know, usually when you're loading things, you want to order by some clause. So someone went in and fixed that and did that. Now that seems somewhat innocuous, but you know, I mean, the change that we're looking for is higher return rates. It doesn't seem immediately obvious why that might do it. But now, as I think about it, I can actually construct a hypothesis. So, you know, is it possible that this change in return rates could be causing higher, or change in order could be causing higher return rates for some products? You know, so just to, you know, kind of give you some background, what I'm thinking, I'm kind of imagining something like this. So, you know, before the 15th, you're seeing, you know, that image on your left is the default. After the 15th, you know, it's the other one, or you know, maybe it's the other way around. All right, so it started with the one on the right, and then went to the one on the left. You know, so I'm looking at this picture and I'm thinking, you know, the vast majority of American males are probably going to look at that sweater and they can know right off the bat that's not going to fit me. I don't care what size it is. I mean, there's a very particular physique there that you know, that fits. You know, and it's possible that, you know, maybe because that was the first picture on there that, you know, people who knew that wasn't going to fit didn't order it. Whereas if they saw the second one, a lot of people maybe ordered it thinking it would fit and didn't find out that it didn't fit until they got it and then they returned it, right? I don't know. Yeah, you know, you can judge for yourself whether that's a plausible hypothesis, but, you know, I think it's worth testing. So how are we going to test this hypothesis? Well, scientific process goes like this. You formulate a question, define your hypothesis, use the hypothesis to make predictions. So if this were to be the case, what are some other things that I might see other than what, you know, I've already observed? You're going to test those predictions empirically. And then you're going to refine the hypothesis and repeat. So science is a very iterative process. When you've done that enough and you feel like you've gotten a good enough answer, then you draw your conclusions. So there's actually two ways to do science. Just for completeness, I'm going to talk about the first as an observational study. So observational study would work something like this. So I suggest if the change in the order of the carousel images is what caused the change in return rates, then it would stand to reason that if there are any out there where the order didn't change, then we would not have seen a change in return rates. So there could be some where the database order just happens to coincide with sorting by update date. And you can also try to find some products that only have one image. And you can go back and you can now look at the data and see did their return rate change. If that return rate did not change, then you've got some good evidence. All right. But at any rate, the gold standard for science is not the observational study, but the controlled experiment. A controlled experiment means that you're splitting your stuff into a test group and a control group. And the control group gets the change. The test group gets the change, the control group does not. So now we can actually construct code that tests this hypothesis in a controlled experiment fashion. I've thrown three possibilities up there. First thing I would probably think of is, well, let's just revert it back to the way that it worked before. But keep in mind that for half the products out there, this was a beneficial change. So I don't necessarily want to do this permanently. I actually want to find out what the problem is. Other than using database order, you could sort by a different key. You can use a completely random order. Now, what's important is that to make this actually work, we need to deploy this to some users, but not others. And note that I said users, not requests, because there's a relationship between the purchase, which happens when they see the product carousel, and the return, which may happen days later. So it's got to be by user, not by request. So we need to find a way to split this. Defining your test and control groups. So this gets back to what I said, what I showed in the very beginning with the structure of the event log. We've put a few things in here that are going to help us do this. So I've included server ID, for example. Easiest way to do this is to use a canary. If you're familiar with the notion of a canary, if you're deploying into large systems, very common practice to put one server out called the canary, get some KPIs off that server, compare that to what you're used to, and only proceed with the rest of the deployment of those KPIs, check out. Checking out means that if there's any differences, they should be differences that you were expecting. It should not be surprising differences. So that's where it's very useful to have lots and lots of servers run the same code. Some other things that are helpful: transaction IDs, user ID, transaction ID, session ID is kind of a triad. Transaction ID in this case is very useful to tie purchases back to, or returns back to the original purchase. In our systems, there's usually one main event, the initial event, and then there can be several consequent events that happen. Transaction ID helps us tie all of those things together. So because this is user-based, Canary process works well only if your requests are essentially partitioned or sharded by user. So if every user is in general always coming back to the same server, then you can use the fact that that's the server that has the control code on it to do your experiment. If you can't get away with that, you can always put branch logic in your code. Now, of course, you have to deploy it everywhere. But then you can split, for example, by taking a mod of the user ID, assuming it's numeric, or hash it and mod it, and split your test and control groups that way. If all else fails, you can use that diagnostic blob that I mentioned. All right. So before I move on, so test and control is always about test group, control group. What about another form of experimentation called, I'm going to call before and after testing? Because this is actually the first thing that we all try, right? Make a change. What's it doing after I made the change? Does it look different? I'm going to suggest before and after testing is not actually a very good approach. Anyone want to venture a guess why? No? All right. So other variables? Sure, yeah. So before and after can get very messy, very messy. Most systems have some sort of like daily peak and trough, right? Your daily traffic goes up and down. And that kind of goes across all your metrics, including return rates. Are probably going to have a little bit of a daily wobble to them. If you do your before while traffic is subsiding, or if you do your deployment as traffic is subsiding, what is your after going to look like compared to your before? It's going to be lower, but it's going to be lower whether you made the change or not because traffic is subsiding. Conversely, if you do it as traffic is going up, you kind of lose that visibility. So it's heavily biased. It's not necessarily bad, and for simple things, we do that. But it's not nearly as effective as a true test and control. All right. So I'm going to wrap up that scenario, and we're going to talk a bit more specifically about what I mean by continuous experimentation. So let's review what our software development lifecycle looks like. So this is kind of a generic, agile process. This is kind of how we all do things now. You start with the initiation of a new product, and then you go into this, continuous cycle of gathering requirements, design, implement, test. I'm trying to be agnostic as to whether we do TDD or not, right? So you're doing design, implement, and test in some order. You deploy it to production, gather user feedback, and then you just repeat that process until you either run out of money or you get bought by Oracle or something, right? Scientific process is also an iterative process, and it actually looks very similar. You formulate a question, define your hypothesis, make some predictions, run a controlled experiment, refine the hypothesis iteratively, and then when you're satisfied that you have a science-worthy result, you draw your conclusions and publish a paper. What are the differences? So the biggest difference comes down to this. They have different goals. So the goal of the software engineering process is to solve a problem. Specifically to solve a problem with code. Produce code that solves the problem. The goal of the scientific process actually is not about solving a problem. It's just about answering a question. And you'll notice that that's actually what we did in our hypothetical scenario. We were not actually trying to fix the return rate problem. We just put code out that helped us understand why it happened. So reverting the order back to what it was before actually isn't any better. It's actually worse for about half the products. It just gets it back to what people were used to. So status quo is very powerful in technical systems. And actually for a good reason. It's totally defensible. People are, building budgets against certain return rates. So if you perturb the return rate, even if you improve it for some and make it worse for others, you mess with people's budgets. But yeah, so the goal was different. And the outcome was different. No matter how that experiment played out, it didn't give us a solution to the problem. It just basically told us that, yeah, that line of code is what caused it. But we can jam these things these two things together and come up with a process that looks a little bit like this, with both the software development process and the scientific process happening in parallel. And if we do that, we can kind of see the links between the two. So the deployment to production is the thing that causes us to draw new hypotheses. New issues come up, and new questions need to be answered, and that kicks off the scientific process, which iterates several times. But the output of the scientific process is not a solution, but input into the requirements for the software process. So once we determine that order is what's causing our return rate change, the next step is to run this through the product process to find out, all right, well, what is the correct thing to do now? It's not, here's the solution. It's what are we going to do next about it? All right, so just to wrap up, I'm going to say a few things that are sort of important to using what I'm calling continuous experimentation. That we employ all of these at Conversant, and they're all things that you can kind of take away. So you can't really do this unless you already have an extremely robust continuous integration, continuous deployment process in place. That means technical infrastructure, but also as a process. If you are doing continuous deployment, the extra thing that you need to do on top of continuous deployment is have the ability to deploy multiple versions just as easily as a single version, and you need to be able to be running these concurrently. Very helpful to do feature branching. I stopped short of saying it's a requirement that you do feature branching, but it's kind of hard to do if you're not doing feature branching. The thing that we use at Conversant that you don't see in most continuous build systems is this notion of the automatic rollback. So this is very helpful. At any average Tuesday at Conversant, we probably have about 5 experiments going on at a time. So that those things don't run unbounded. We have a process in place that automatically reverts them all to the production version at the end of the day, end of the business day. Unless you go into a configuration and give it special permissions to be a long-running experiment if you need to do that. So those are some things that are helpful. Second thing that you need to do is around culture. First thing, you got to be comfortable with throwing away code. That scientific experiment code is not meant to be permanent. You're answering questions, you're not providing solutions. A lot of developers, a lot of bad developers, hate to throw things away. And that's something that you got to get out of people's heads. You got to get comfortable. Write it, throw it away, write it again, throw it away, write it again. It's not going to take you nearly as much time to write it the second or the third time as it took you the first time. Top to bottom, culture of experimentation. That means it's not just engineers, but your product managers, stakeholders, and in some cases even your partners' clients need to be on board with this, so people understand what the expectations are. And then the one last point, which is almost as important as any of them that I want to throw out there, is needing to know what's off limits. So testing and production is dangerous. What we do at Conversant is extremely dangerous. Because of our exposure, we're one of a small handful of companies that can literally break the internet if we put out bad code. In fact, a couple of years ago, one of our competitors did just that, put out bad code and broke like 2/3 of websites out there. So we have to be very careful. But something else that's very dangerous, open heart surgery is dangerous, right? Brain surgery is dangerous. But how did we get to all of that? Well, we did it with careful scientific experimentation and a code of ethics, right? So in your own environment, you need to know what those things that you just can't touch are. Similar to the way scientists, we would probably have a cure for cancer by now if, scientists weren't so, sensitive about sacrificing human lives for science, right? Good chance that you've got a similar thing in your own environment. You just need to know what that is and develop that code of ethics so that people know you don't mess with that. And then building a culture of scientific experimentation, I think, would be a great advancement for everyone. That's what I got. Thank you. Questions?